Hey everyone, and welcome to this study guide explainer. If you're knee-deep in university-level quantum physics right now, you already know that trying to bridge the gap between that rigorous, heavy quantum mechanics and, actual geometric intuition is absolutely essential for your exams. And let's be totally honest here, the math can be incredibly dense. But that is exactly what the Bloch sphere fixes. It's a real game changer. Today, we are going to unpack this incredible tool and translate the raw physics of qubit states directly into a beautiful visual geometric model. Let's dive right in. So, here's our quick roadmap for today's explainer. First, visualizing the sphere. Second, the phase-spin analogy. Third, spin angular momentum vectors. Fourth, deriving the state equation. And finally, number 5, opposite points and bases. All right, let's jump right into part 1. Visualizing the sphere. So what actually is the Bloch sphere? Basically, think of it as a graphical, three-dimensional representation of a qubit state. The absolute most important thing to grasp here right off the bat is the vertical layout. Right at the very top, the North Pole, we have the Ket 0 state. And all the way at the bottom, down at the South Pole, we have the Ket 1 state. Where your qubit physically sits in this 3D space directly dictates the exact probability of what you'll get when you actually measure it. Let's compare these spatial positions for a second, because there's a direct inverse relationship happening along the vertical axis of the sphere. The closer your qubit state is to the top, so the higher its latitude, the higher the probability that you're going to measure a 0. Conversely, the lower the qubit sits on the sphere, sinking down toward that South Pole, the more likely you are to measure a 1. It's a beautifully intuitive way to just visually see probability mapped straight onto physical space. Let's walk through a really concrete example. Take the state 1/2 Ket 0 plus √3/2 Ket 1. If we map this out mathematically, that 1/2 gives us a 1 in 4 chance of measuring a 0, right? And the √3/2 gives us a 3 in 4 chance of measuring a 1. Because it is significantly more likely to be a 1, this point doesn't sit anywhere near the top. Geometrically, it lies completely below the equator, literally exactly halfway between the equator and the South Pole. Okay, moving smoothly on to section 2, the phase-spin analogy. I absolutely love this quote from our source material. It says, "Since it is a sphere, the qubit can spin around the sphere. This is called phase." Give yourself this vivid mental analogy right now. Imagine the qubit physically spinning around that central vertical z-axis. While the up and down latitude tells us our probability of measuring a 0 or a 1, that horizontal longitude, where it sits as it spins around the equator, dictates the quantum phase. Next up, section 3, spin angular momentum vectors. Now, it's time to zoom in a bit on the raw quantum mechanics. Here we're mapping the absolute foundation for the math we're about to do, the spin measurement operators. That's Sx, Sy, and Sz. As you can see, to get these spin operators, you simply take the Pauli matrices sigma x, y, and z and multiply them by the constant h bar over 2. These operators are how we actually calculate the spin angular momentum of our particle along the x, y, and z axes. Now, here's where it gets kind of wild. Whether you measure along the x-axis, the y-axis, or the z-axis, the resulting eigenvalues remain exactly the same. No, really. If you set up the determinant equation to solve for the eigenvalues of these spin matrices, they will always resolve to plus h bar over 2 and minus h bar over 2. The eigenvalues are completely independent of whatever arbitrary direction you choose to measure. But you might be wondering, why are we setting up these specific calculations? Well, a qubit doesn't just sit perfectly on the x, y, or z axis all day, right? It can be literally anywhere on the sphere. To measure spin in an arbitrary direction, we have to use a dot product, the spin vector s dotted with an arbitrary unit vector n hat. By doing this, we can figure out exactly how any arbitrary point on our Bloch sphere translates into a standard coordinate system using sine theta and cosine phi. And that brings us perfectly to section 4, deriving the state equation. Let's walk through this core logic step by step without getting bogged down in every single algebraic fraction. Step 1. You just set up your standard eigenvalue equation, operator times state equals eigenvalue times state. Step 2. You use that positive h bar over 2 eigenvalue we just talked about to solve for your y variable in the matrix. Step 3. You plug that back in to form your initial eigenvector. Now, step 4 is absolutely crucial. In quantum mechanics, we really don't like leaving our eigenvectors full of fractions. To clean it all up and finalize our vector into standard form, we purposely remove those fractions, in this specific case by multiplying everything by the cosine of theta over 2. Actually, quick aside before we look at the final equation, let me clarify a super common point of confusion for students: the global phase, represented by e to the power of I gamma. We actually mathematically ignore this global phase entirely. Why? Because when we apply unitary operations, the phase perfectly cancels out. It appears as positive on the ket side and negative on the bra side, multiplying out to 1. So it has absolutely zero observable significance, leaving us solely focused on the relative phase for our computations. And boom, here is the payoff. The crucial point is this final, elegant result, the generalized qubit state equation. Cosine of theta over 2, ket's 0, plus e to the power of I phi, sine of theta over 2, ket 1. This equation is the ultimate bridge. It takes all of that heavy linear algebra, the eigenvalue fractions, the dot products, and links it directly back to a simple geometric point on our Bloch sphere, defined perfectly by just the angles of theta and phi. Finally, let's wrap things up with Section 5, opposite points and bases. Let's zoom out again for a second. What happens if you take a point on the Bloch sphere and want to find its exact geometric opposite, mathematically? You use a really clean system of logic. First, you substitute your polar angle theta with pi minus theta. Then, you substitute your azimuthal angle phi with pi plus phi. Finally, you apply standard trigonometric conversions. For instance, the cosine of 90 degrees minus theta over 2 mathematically converts straight into the sine of theta over 2. It cleanly flips the mathematics of our quantum state. And this brilliantly illustrates one of the absolute golden rules of quantum computing representation. Two geometrically opposite points on the Bloch sphere perfectly represent orthogonal basis states. If you calculate the exact geometric opposite of your plus eigenvector state using the substitutions we just walked through, you perfectly yield the orthogonal minus state. It beautifully unifies the rigorous math and the intuitive visual sphere. The North Pole 0 state is orthogonal to the South Pole 1 state, just like opposite ends of the x-axis represent orthogonal basis states. Wow, okay, we have covered a ton of ground today. We've visualized the sphere, conquered the spin matrices, derived the state equation, and proven how opposite points map to orthogonal bases. But I want to leave you with a provocative thought as you continue your physics journey. Now that we thoroughly know how a static point cleanly maps to a state equation, what mathematical operators are required to actually move a qubit across the sphere? How do we dynamically force our qubit to travel from the North Pole all the way down to the equator? Think on that, because that is the fascinating world of quantum gates, and it's precisely what you'll be studying next. Keep up the great work, and happy studying.